Hi, my name is Alina Kachaki. I'm a member of the IceCube group at Michigan State University. Today I'm going to be talking about some work I've been doing projecting diffuse sensitivity with IceCube-Gen2. Okay. Oh, is that set up? Should I be clicking here? Great, okay. So I'll just give sort of a rundown of the current experiment. I'm pretty sure most people are familiar. This is a cubic kilometer of South Pole ice, which has been instrumented with about 5,000 digital optical modules. Deployment of the first 86 strings was completed in 2010, but we're continuing now with a low energy upgrade, which will begin deployment as well in 2023. I think we've already sort of covered the detection technique a few times today, but I'll just sort of touch on it again quickly. We have charged leptons, which are produced either in the atmosphere or locally in the medium around the detector in neutrino interactions. These pass through the ice and generate detectable radiation, okay? Generally, there's two sorts of light depositions that we talk about. We have both extended tracks, okay, and these have good angular resolution. And we also have cascades, and these are point-like energy depositions, and they have very good energy resolution. Okay. So IceCube has been running for over a decade at this point. There have been a number of discoveries that have come out of it, really since it's begun running and in the past few years as well. In 2013, it established the existence of the actual astrophysical neutrino spectrum. Following that, in 2017, it observed its first point source. This is TXS 0506056, a transient neutrino source. Recently, we've also been noticing with different analyses of the diffuse astrophysical spectrum, we actually see some tension in measurement of it. Okay, and so that is this. I'm gonna try pointing. This points, right? What do I press? Okay, it's not working for me. Oh, okay, sorry. So in this plot down here, okay, this is just showing 3 different measurements of parameters of Howard law parametrization of the astrophysical spectrum, and you can see there is quite a bit of difference in these different selection methods and the result you get for those parameters. Okay, and then of course people are familiar as well. There have been a number of source searches, and none of these yet have actually explained the entirety of the diffuse spectrum in a significant way. Okay. Okay, so this sort of brings us to IceCube-Gen2. This has really been motivated by trying to further understand point source science and neutrino astronomy. But you know, in addition to this, many of the features that this detector offers are also beneficial for study of the diffuse spectrum, okay, so beyond point source science. In general, this is an 8 cubic kilometer detector, okay, so going up about an order of magnitude in size and volume. It will be 120 additional strings deployed around the existing IC86 detector. We're expecting about a factor of 2 improvement to angular resolution, and then increases in both track and cascade statistics. Okay. My presentation will really focus on Gen2 optical. This is the in-ice component of the detector here, but I'll point out there's also a Gen2 radio array and a Gen2 surface array planned, okay? And so sort of the synergy of these 3 things allow us to study different sources of neutrinos. We have astrophysical, atmospheric, and cosmogenic. I can't cover this in more detail here, but Anna Nels will give a poster on Thursday, which will cover Gen2 more widely. Okay. So there are a number of reasons really to look into the diffuse spectrum to help us understand our actual point source populations, okay? In general, looking at spectra in the energy, looking at structure in the energy spectra can clue us into source type and environment, as well as the energy budget of these sources, okay? I don't have time to cover everything on this slide, but I'll also say sort of in the wider picture here, IceCube-Gen2 is sort of a necessary extension to IceCube because it does increase high energy sensitivity. And this sort of lets us complete the multi-messenger picture here. Okay, I'll talk about the 2 types of studies that I've performed now, okay? So in general, IceCube observes muon background as well as conventional and prompt neutrinos, which are produced in air showers, in addition to the actual signal, which is astrophysical neutrinos. Okay. This work focuses on sort of a simple diffuse study looking at first order systematic effects to measurement of a power law astrophysical diffuse spectrum. Okay. So I'll just make it clear, the systematics included here were the prompt and conventional normalizations. Okay. And so then I've gone ahead and performed 2 benchmark analyses based off of current IceCube analyses. So I performed both a Cascades focused analysis and a Northern Tracks analysis. Okay, and I will be showing sensitivities, and I'll just say here, I will be comparing with a very similar IceCube analysis which was performed and the sensitivities that that analysis has produced. Okay. So this is just sort of a rundown of the actual selection process for the Cascades analysis set. So it begins with the number of quality cuts, and then I've also trained a gradient boosted decision tree on event topology. Okay, so we have both Cascades as well as starting and through going tracks. I've then used the result of this model to derive an analysis level selection. Okay, and the resulting effective areas are pictured here on this slide. Okay, so for IceCube-Gen2 at these highest, TeV and PeV energies, we do see about an order of magnitude increase to effective area. Okay, on this slide, I just have sample spectra from the actual selection plotted at 10 years of lifetime. Okay, so on so on the left here, these are events from the entire selection, so from the entire array. Okay, so these were picked up on the 120 additional strings plus the existing 86 IceCube strings. Okay. On the right here, this is a subselection of those events. Okay, all of these events have reconstructed cascade vertices within the perimeter of IC86. Okay, so IC86 or the present IceCube has a slightly finer string spacing than what Gen 2 will have for the newer 120 strings. So the angular resolution will be a bit different. And so I've made these 2 cuts on position here. Okay. I'll also emphasize, due to computational limitations, we weren't able to model the full passing muon spectra, okay, of this selection. And so normally what would happen if we're doing a high statistics analysis, we would have this spectra, and we would also derive a control sample based off of classified through-going events. Okay, so this would let us constrain the actual normalization of the prompt spectra, and it wouldn't really be a major impact to sensitivity for this analysis. Okay, so it was included in the BDT that I've used, but then it's not being included in the fit here. Okay, here is the actual result for the Gen 2 Cascades analysis. Okay, and I'll just emphasize, I've again used a slightly different likelihood than what's usually used. Okay, so nominally we have both energy and zenith bins in the likelihood, but I've also added in a positional bin. Okay, so we have both reconstructed vertices in IC86 and IceCube, and all others outside. Okay. So then I have this 10-year sensitivity pictured here, and it is pictured with like a current IceCube sensitivity in blue, okay? And I'll just note on this slide, the angular resolution right now is fairly conservative, okay, what's being used in this study. This is something I need to go back and fix. It is a work in progress. I'll explain the impact of that on the next slide. Okay, on this slide is the actual combined diffuse result. Okay, so I also have the Northern Tracks sensitivity pictured here as well. Okay, and so for that analysis, I've used muon charge current events. There is a small, step down in sensitivity because I haven't included tau-induced tracks. And I will just say there is potential for the Northern Track selection to improve. Really, it's based on optimizing quality cuts at this point. Okay. Okay. I just want to highlight here, okay, so you see this elongation in the Cascades contour, okay, sort of along the positive diagonal here. And so what that's caused by right now is degeneracy between the prompt astrophysical spectrum, the prompt atmospheric spectrum and the astrophysical spectrum, okay, degeneracy between those two spectra. Nominally, we don't have such a large degeneracy. In a normal analysis, we veto atmospheric events, and so naturally, prompt and astrophysical events are removed from the selection, and this is sort of a zenith-dependent effect. Because there's this zenith dependence added into the expected distributions, this lets us better constrain the prompt and the astrophysical, okay? So this is really dependent on angular resolution. Okay, so these present results give sort of a first estimate of diffuse sensitivity for a 10 cubic kilometer volumetric neutrino observatory. Improvements are really driven by cascade sensitivity and statistics beyond 1 TeV, okay? After the angular resolution is sort of patched and fixed in this analysis, we're expecting about an order of magnitude decrease of the original IceCube contour. Okay, just as like a final closing statement, in general, Gen2 will offer a precision measurement of the diffuse energy spectrum, okay, and that's sort of been shown through this work. But there's also a lot to see with its ability to measure spectral structure as well, okay? And this will really be the focus of future work and sort of extend the science program beyond IceCube, okay? And that